Okay, so in this video, we're going to look at a concept called binding energy. Now, binding energy is possibly one of the most challenging things to get your head around because it's not usually what people think it is. So binding energy ties into nuclear decay because effectively this is going to be a source of energy in some respects that is given off when we undergo either fission or fusion. And these processes are very, very specific, and we're going to talk about them individually, and hopefully we'll get onto something called the binding energy curve as well. But we'll probably leave that for the next video entirely. So let's start out with just a straight up definition of binding energy. So it's an amount of energy required to separate a nucleus into its constituents. Okay, so what does that mean in terms of a drawing? Well, say we have a nucleus that's all bound together with protons and neutrons. In order to get that apart, in order to separate it into all of its constituent parts, you're going to have to put energy in. You're going to have to put energy into that situation. It's kind of like if you've got a big rock and you want to break up that rock, and you take that rock and you throw it on the ground. You'd put energy into it to break it into all its constituent parts. And if you smash it on the ground hard enough, it will smash into all of the smallest pieces possible. And that's effectively what we're doing here. We need to put a certain amount of energy in, i.e. the binding energy. And when we put that energy in, then we split it into its constituent parts. And what you'll notice is this is very kind of like a fission situation. But one thing I will make very clear straight away is that try not to get confused in future videos about this concept and fission and fusion. Okay, this is just helping you to define the binding energy. We would never really do this. We would never put in energy and actually separate it into all its constituent parts. This is just a definition of the value for the binding energy, because binding energies are going to change. And that amount of energy you would have to put in would change. Common misconception: binding energy is not the energy you get out of something. It's an amount of energy you have to put in. And so, more often than not, they are represented by negative numbers. But we'll talk more about that when we talk about the binding energy curve. So it's the amount of energy you need to put in order to separate it into its constituents. Now, one thing you need to be aware of here is something very, very strange happens. And it's going to wig you out a little bit, but we're going to need to explain why it happens. Now, as a result of putting this energy in, all of the constituents and them all joined together weigh and have a different mass. One of these is going to be heavier than the other. They're going to have more mass. Okay, so have a think which one you think that is. Is it going to be them all separated? Is it going to be them all together? Well, the correct answer is they have more mass when they are all separated. Now that might be very, very odd for you to get your head around because you don't have a concept yet of Einstein's energy equation, which is otherwise known as E is equal to mc squared. Now this equation is very, very poignant and very useful because it explains why we have more mass here. Because energy and mass are almost synonymous. If you have a certain amount of energy that you've got, it's come from a change in mass. So actually, the change in energy is equal to the change in mass times by c squared. And that's often how we write this equation to be a bit more correct. And notice the c squared value there. This c is the speed of light, which is 3 times 10 to the 8. Okay, 3 times 10 to the 8 meters per second. So obviously we need to square it. So bear that in mind. This equation is going to come into place. When we put energy into this situation, that energy has to go somewhere. You've put energy in, it can't be lost or destroyed or created. That's conservation of energy. It has to go somewhere. And it's not going to heat. Well, it might go a bit to heat, but in this circumstance, we're putting in energy, and that energy's got to go somewhere. And so what happens here is that change in energy, that energy that you put in, becomes the change in mass with respect to c squared. So you could almost write this as the gain in mass is equal to the energy that we put in divided by c squared. And that's how much more this would weigh, because you've put energy into this situation. So you put energy in and you got it out. Now, interestingly enough, we could think about this backwards. If we were to take all these constituents together and force them together, then effectively they would lose mass. Sorry, it's just one I would lose. They would lose mass, and as a result, that loss in mass would give an amount of energy that would be given off in this circumstance. Okay, so that's your basic understanding of what binding energy is and how binding energy works. You will obviously probably have some questions about that idea, and that's good, because obviously it's not an easy concept to get your head around. But in summary, you put energy in, that's the binding energy, the amount of energy you need to split into its constituents. That separates it into its constituents. It has more mass because that energy has to go somewhere because of Einstein's energy equation.